Let's take a look at the solution to number 1. What's required for an object to move in circular motion? Well, you should know that a net inward force is required. We call that the centripetal force. And so it might be a good use of your time right now to pause the video and try to draw a free body diagram for the block when it's at the location shown. In the back of your mind, you need to remember that it better have a net inward force since it is going in a circle. So give that a shot first, and then we'll continue along. All right, so hopefully you got it. I'll come over here, and we know that we have gravity pulling down, the force of gravity, and we have the normal force pushing up. Those are going to balance out. There's no acceleration in the vertical y direction here. But we do have this inward force pointing towards the center of the circle. And that's going to be the force of static friction. It's not kinetic friction. Even though the object is moving through space, it's not sliding across a surface. That's what's meant by kinetic friction. Static friction just means that the block itself is not moving relative to the surface itself, and it's certainly not moving relative to the surface. Both it and the surface are moving around in a circle. All right, so there's the free body diagram, and the only force that is radial is this static friction force. So we really only have one thing to deal with over here on the right-hand side. So we'll write that in, the force of friction static. Okay. Now that better be equal to the mass of the object times the tangential speed squared divided by the radius. So that's the mathematical condition that has to be true at any moment in time if this thing is moving in a circle. Now the whole point of this question is about this maximum speed. What's the fastest it can go, right? Well, think about what static friction was all about. If we have, two objects that are trying to rub past each other, static friction arises. It's a force, right? And it can go from 0 newtons all the way up to some maximum value as the surfaces of the two objects kind of interlock, and eventually they're going to give if there's enough push on the object. So eventually what's going to happen is if this thing spins up too fast, the block will slip and it will not be going in a circle anymore, and we wouldn't call that static friction. And so this static friction force is going to go from a small value to a larger and larger and larger in value as the platform speeds up and goes faster and faster, but it will reach a maximum amount. So we'll write that out here and remember that the force of friction static maximum, what was that equal to? Well, it's equal to the coefficient of static friction times the normal force. And in this problem, that's pretty simply equal to mu s times mg, because the normal force is balanced out with the force of gravity. So the maximum amount of static friction we can get is given over there. And if we plug that in now, we are plugging in for the condition that we have the largest amount of inward force that friction can ever provide. And so that's going to be the fastest we can ever go around without slipping. And so we'll put the subscript Vmax there. And then we'll also plug in for our radius with the constant that we're just using, a capital R, to represent some number that we're not specifying. And now I think you can do the rest of the math, so maybe pause the video and give it a shot and see what you get for the maximum speed that this block can be moving at. All right, so we'll just step through the math a little bit here. It's pretty easy. Interestingly, the mass cancels out, and we end up with Vmax is equal to the square root of the coefficient of static friction times the gravitational field strength times the capital R, which is that radius for the object. So we now have a relationship that allows us to calculate the fastest a block would ever be able to go if placed at some distance away from the center of the platform in a gravitational field with some coefficient of friction. Now here's a follow-up question. And this will be before we get to number 2. What happens if we came along and we placed an object at location A that was identical in every way, except it was just twice as massive. So right now we have a mass of just m. But what if we could make this twice as massive? Obviously, it would be more dense if it's the exact same physical dimensions, just to make everything constant. But make a prediction, and would this maximum speed now be any different? Would the maximum speed be larger? Would we be able to go faster before slipping? Or would the maximum speed be less? Or maybe the maximum speed wouldn't change at all. Okay, pause the video and apply what you've learned here. Okay, so hopefully you thought about it, and it's really a pretty simple answer once you have actually used first principles and derived this relationship over here. And you can clearly see that there is no mass value in this equation at all. So this prediction for how fast you can go right before slipping on this platform has nothing to do with the mass. So you could put any size mass here you want, and it would slip at exactly the same speed. That's kind of cool. So you could speed this thing up, and if you go a little bit faster, you'd see this thing slip, and then you could take something that's like 10 times as massive, put it at the same spot on the platform, spin it up, make it go faster, 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 and then right when it gets to that same maximum speed, that thing will slip exactly at the precise time as well. So pretty cool little outcome. Awesome. All right. In the next video, we'll take a look at the question 2 and the solution to that.